Hello class. Today we will continue chapter 2 with section 2.2. We will continue our look into set theory, and today we will look at subsets. Our objectives today are to recognize subsets and use this notation. This notation stands for subset. We also need to recognize proper subsets and use the notation for proper subsets. And we need to determine the number of subsets of a set. Now, the definition of a subset of a set is the first thing we will look at. Let me get my pen set up here. Set A is a subset of set B, expressed as A is a subset, this meaning subset, of set B. If every element of A, or in set A, is also an element in set B. The notation A is not a subset of B essentially uses the same style notation but puts a dash here through it to let you know it's not equal to, or is not a subset of B. A is not a subset of B. Set A is not a subset of set B if there is at least one element of set A that is not an element of set B. Every set is a subset of itself. Every set is a subset of itself. So let's look at some examples. Example 1, using the symbols subset and not a subset. We want to write the symbol for subset or not subset in the blank to form a true statement. So let's look at sets A and sets B. Set A here is the set 1, 3, 5, and 7. Set B is 1, 3, 5, 7, 9, 11. We have to ask ourselves, are all of the elements in the set A also in set B? Let's check. 1 is an element of A. 1 is also an element of B. 3 is an element of A, is also an element of B. 5 is an element of A, is also an element of B. 7 is an element of A, is also an element of B. So, A is indeed a subset of B. A is a subset of B. Very, very nice. And we can use some better notation here, drawn by the computer rather than myself. So, I'll erase it so you can see it clearly. It agrees that A is a subset of B. Let's look at B. B says A equals X such that X is a letter in the word proof. And we've got a little incorrection here. Let me correct my PowerPoint here. This is set B. B equals Y such that Y is a letter in the word roof. So, as I look at this, we want to know, is A equal to B? I apologize for the typo in my slide here, but this is set B. So, let's think about this. Now, the way that I'm going to do this is I'm going to write out my roster set over here to the right hand side so I can compare. Now X is a letter in the word proof. Okay. So that would mean that X is the set P, R, O, and F. Remember, we we do not have to, and we're not supposed to repeat elements. So that's why I only have to write O once. If I rewrite this set, so this is our A set, this is our B set, written in our roster notation, this is R, O, and F. So, is A subset of B? Well, does B contain every element of A? No. A has this letter P. B does contain the R, the O, and the F, but it does not contain the P. Therefore, A is not a subset of set B, which can be written not a subset. So, that is our notation for not a subset. Now we need to define what we call proper sets. The definition of a proper subset of a set is set A as a proper subset of set B expressed as A as a proper subset of B if set A is a subset of set B and sets A and B are not equal. If you will notice, the difference between proper subset notation, which is this means proper subset, this means subset. The only difference between the two is a proper subset does not contain this equal to sign down here below the subset notation. So a proper subset cannot be equal because we leave that equal sign off. That's how we distinguish between our notation here. So if we look at an example, example 2 says, using the symbols subset and not a subset, we want to write subset, proper subset, or both in the blank to form a true statement. So let's look at this. A such that X is a person and X lives in San Francisco. Set B is X such that X is a person and X lives in California. Alright, let's think about this. We want to know, is A subset or a proper subset or both of set B? If a person lives in San Francisco, does that person live in California? Yes. Yes, they do. San Francisco is in California. Now, that definitely means that A is a subset of B. So we're confident here. We are confident. I'm going to rewrite it over here. We are confident that A is a subset of B because if you live in San Francisco, you live in California. To determine whether it's a proper subset, we would have to determine, can there be elements in set B that are not in set A? Because we don't want them to be equal. A should be a smaller set of set B. And if we think about it, San Francisco is not the only place in California. So you could have somebody that lives in California but doesn't live in San Francisco. But you cannot have somebody that lives in San Francisco but doesn't live in California. That means, take a minute to think about what I just said. That means that A is also a proper subset of set B. Because A and B are not equal. So your solution here is that A is a subset and a proper subset of set B. It can be both. Okay. It can be both. Okay. Anything that is a proper subset of something is also a subset of something. But just because something is a subset of something doesn't mean it's a proper subset of something. I'm going to say that one more time. If something is a proper subset of something, then it definitely is a subset of it. But if it is a subset of it, it doesn't mean that it's a proper subset of it. Let's look at another example. A is 2, 4, 6, 8. B is the set 2, 8, 4, 6. Is A subset of set B? Well, is every element of A and B? Yeah, there's a 2 here, there's a 2 here, there's 4 here, there's 4 here, 6 here, 6 here, 8 here, 8 there. So A is a subset of set B, no doubt. But is A a proper subset of set B? This means that A is a subset of B, but it means that A and B aren't equal. Do A and B have all of the same elements? Are there any elements in B that aren't in A? No. So because A and B are essentially the same thing, the only difference here is order. And remember, order does not matter in sets. Because they're the same set, you cannot say that they're proper subsets. So the only solution here is that A is a subset of B, but A is not a proper subset of B. Let's look at subsets and the empty set. The empty set as a subset. For any set B, the subset is an empty set. For any set B, the empty set is a subset of B. For any set B other than the empty set is a proper subset of B. Okay. What this means. The empty set is a subset of any set. You can find some nothing in any set. Okay. It might have some something in it too, but you can find some nothing in any set. And as long as the set itself isn't completely empty, it has something else in it other than nothing, then the empty set is a proper subset of that set. That is essentially what 1 and 2 say. The number of subsets of a different set. Now, this is where it gets interesting. If we look at the empty set has no elements. So, if we list all of the distinct subsets of the empty set, we can only list one subset, and that would be the empty set itself. Therefore, we have one subset of the empty set. If we look at the set A is basically a set that contains one element. And we need to list all of the distinct subsets of that set. We can list the set itself, the set of A, and we can also list the empty set. And that is 2 sets that we can list from that one set. Remember, empty brackets here is just the empty set. I want to make that clear. This means the empty set. The empty set is in every set. Okay. If we look at a set containing 2 elements, here it's A and B. If we want to list all the distinct subsets, we have to list the set A, B itself, and each individual element of that set is also a set of itself. So we're listing the set AB, we're listing the set A by itself, the set B by itself, and also the empty set that resides in there as well, because the empty set is in everything. There's a little bit of emptiness in us all sometimes, I guess. So, counting up the number of distinct subsets of a 2-element set, we see that there are 4 subsets of a 2-element set. If we continue this trend, and we have 3 elements in the next set, A, B, and C, and we want to list all distinct subsets of this set here, we have to start with the set itself, ABC. We can then break it down into sets of 2, a set of AB, a set of AC, and a set of BC. Remember, the order doesn't matter, so I can't go changing the order here and creating a new set, because the set CB would be the same as the set BC. So order does not matter here, which is why we're only winding up with 3 combinations here. Because, like I said, the set BA is the same as the AB because order doesn't matter in sets. So don't switch the order and think you have a brand new set. We also have the individual element sets, A, B, and C. And once again, we have the empty set. If we add these together, we have 1, 2, 3, 4, 5, 6, 7, 8 possible subsets of this initial 3-element set. As we increase the number of elements in the set by 1, the number of subsets doubles. The number of subsets of a set with n elements is 2 raised to the n. The number of proper subsets of a set with n elements is 2 to the n minus 1. We can prove this. Okay. Remember, a proper subset means that it's not the same size as the initial set. Okay, that's why we have to subtract that initial 1. But if we want to know the number of subsets here, it's essentially 2 to the n. N here is 0. 2 to the 0 is 1. 2 to the 1 is 2. 2 to the 2 is 4. 2 to the 3 is 8. Remember, I'm getting each of these exponent numbers over here from the number of elements in the sets. This is the number of subsets. The number of proper subsets would be this number minus 1. Let's find the number of subsets and proper subsets. Find the number of distinct subsets and the number of distinct proper subsets. Because we now have the equation, we do not have to make a list of these subsets and proper sets unless the question specifically asks for it. We know that there are, if we're looking for subsets, we know for subsets that the equation is 2 to the n. How many elements are in here? 1, 2, 3, 4, 5. We have 5 elements in this set. So this tells us that the number of subsets we have should be 2 to the 5th power. Now 2 to the 5th power, that's 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, times 2, which is 32. So we should have 32 subsets here. We also want to calculate the number of proper subsets. The number of proper subsets is 2 to the n minus 1. This is 2 to the 5th minus 1. Remember, 2 to the 5th is 32. We've calculated that already. If we subtract 1 from that, we see that there are 31 proper subsets. Just like that. We have the equation. We're going to use the equation so that we don't have to write out every single combination, because we would have had to have written out 32 combinations here of sets if we didn't have the formula that we derived. Let's erase this so we can go on to the next part of the problem. So I'm going to erase this work, pause if needed. I'm going to erase this work so we can go on to part B. Okay. Alright, now B says x such that x is contained in the natural numbers, or is a set of the natural numbers, and 9 is less than or equal to x is less than or equal to 15. Let's write this out in roster form. 9, 10, 11, 12, 13, 14, and 15. By writing it out in roster form, it makes it a lot easier to see the number of elements in the actual set. Here, it's 1, 2, 3, 4, 5, 6, 7. So the cardinality of this set is 7. Okay, 7. So, if we want to know the number of subsets, so I'll write it right here, we need to do 2 to the 7th power. 2 to the 7th power is 128. If we want to know proper subsets, we're going to look at 2 to the 7th minus 1. That's going to be 127, because 128 minus 1 is 127. So by knowing the number of elements in a set and knowing the formula for the number of sets, subsets, and proper subsets, we can make a problem that would have been very hard to list very simple. Now, the number of subsets of infinite sets. There are x to 0 natural numbers. So it has 2 raised to the x to 0 subsets, which has your basically x to 0 minus, or 2 x to 0 minus 1 proper subsets, which we're going to see is 2x to the 0 is greater than x to the 0, which is denoted by x to the 0 by x sub 1. X sub 1 is greater than x sub 0, therefore x sub 0 is the smallest transfinite cardinal number in the infinite hierarchy of different infinities and beyond. So says Buzz Lightyear. Don't worry so much about this last slide. It was just to expand your mind here and show you that there are indeed subsets of infinite sets. We should know this. You can make a subset of infinite set, and if you look at the number of subsets of a particular infinite set, that itself is most likely infinite. And the number of proper subsets itself is also infinite, but the number of subsets will be greater than the number of proper subsets. Therefore, we'll have a whole bunch of subsets. Okay, it's just a broaden your mind style thing here. Anyways, this is the end of chapter 2.2 lesson. If you have any questions, please don't hesitate to reach out to me and ask me any of these questions. Please go on to attempt your chapter 2.2 homework on my math lab, and I will see y'all for chapter 2.3 next time. Y'all have a good afternoon.